right, so we're starting our new chapter, which is all about exponents and logs. And section 1, we're just going to focus on the exponential functions, okay? Like stuff to the x. You ready? And so we are going to first go over some graphs of stuff to the x, and I thought it might be nice to start with 2 to the x. And then maybe talk about 3 to the x. Maybe even try a fraction to the x, just for fun. Okay? Okay, so on your note sheet, you'll just notice that exponential functions are a to the x. A has to be bigger than 0 because we don't want to do negative numbers to a power, because then it alternates positive, negative, and the graph would look so crazy. So we're going to keep our bases of our exponential functions positive. We're also not going to really talk much about them being 1, because 1 to the anything is? Say it loud. 1. Good, so that would be a boring graph too. So let's start with 2 to the x, and let's make ourselves a little table. And I just want you to actually figure out 2 to the each of these numbers. Can you do that? Do you guys remember what 2 to the negative 3 does? Yeah, it reciprocalizes it, right? So 2 to the negative 3 is the same thing as 1 over 2 to the 3, which turns out to be 1 over 8. Good. And 2 to the negative 2? 1 over 2 squared is 4. That's annoying. To the negative 1. Good. 2 to the 0? 1. 2 to the 1, 2 to the 2, 2 to the 3. Yes? Yeah. Yes! And then we can graph those. Okay, go ahead, graph them. Did I screw anything up there? Do you guys remember learning about functions that look like this? Was it an Algebra 2 thing? Slightly, they think they've seen this before. Okay, so this is a graph of 2 to the x. It's kind of a parent function. So now we could do all kinds of 2 to the x functions, slid around and stretched out and stuff. What was your comment? Never mind, okay. Okay. Can you guys help me describe what the ends of the function do? Like, how about this end, where x goes back to like huge negative numbers? What's the y value doing? What is it doing? Shrinking, 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 shrinking down to fractions and smaller and smaller and smaller fractions. It never will get to 0. But it's trying, right? What's that called? If it's going, yes, an asymptote. What sort of asymptote? Yes, in fact, 2 to the x does have a horizontal asymptote, describing its end behavior at the high negative x values. But then what happens when you go to the big positive x values? Yeah, like really fast, actually. It grows exponentially. That means really fast. And it grows super huge up to infinity. Okay, so it does have a horizontal asymptote, but that only applies to one side of the graph. Identify any asymptotes. I think we just talked about how it has a horizontal asymptote. What's the equation? Good. Y equals 0. Yep, that dotted line I drew is y equals 0. How about a vertical asymptote? It kind of looks right now like there could be a vertical asymptote, but if you think about it, there's not really any number that we couldn't use as a power. You know, there's no, like, what's the domain of this function? 2 to the, can't you pretty much plug anything into 2 to the? So there is not going to be a vertical asymptote. It only looks like that because it's growing so fast, but it actually continues growing for all of the x values. So there is no vertical asymptote. Fascinating, huh? Yeah. Are you enjoying this? Good times? All right. Oh, you know what would be fun? If we compared the graph of 2 to the x to the graph of 4 to the x? Okay, so why don't you throw down your 2 to the x on this second graph too? I'm going to use red. Did you do that really fast like me? Because it's a parent function now, so I'd sort of expect you to be able to graph 2 to the x in 10 seconds or less. Do you think you could do that? Maybe with a little practice? Okay, lovely. Now let's do some 4 to the x. I'll switch colors. If you have colors, you could switch. How about blue? How about a pretty blue? Okay, so I'm not going to make a table. I'm just going to think in my head. Are you okay with that? Okay. Great. Thanks for agreeing. 4 to the negative 3. 1 over, what's 4 cubed? I don't think so. 64. 1/64. That's tough to graph. How about 4 to the negative 2? Which would be 1 over 4 to the 2. 1/16. Still super tiny. How about 4 to the negative 1. 1 over 4. Good, so 1/4. Now it's getting a little easier. Did you notice those are all underneath the graph? Yeah. What's 4 to the 0? True story. 4 to the 1. 4 to the 2. Oh dear. Okay, well, let's connect our dots then. Isn't that interesting how the base, only changing from a 2 to a 4, it grows so much faster once you get past that y-axis, you know what I'm saying? Fascinating. Okay. So is it true that the red graph is ever greater than the blue graph? When? Where? Show me where. Right over here. That's when that happened. The red graph was greater than the blue graph. For what values of x? For x's, good, less than 0. But then sometimes 4 to the x is bigger than 2 to the x, right? For when? Over here. Good. Why is that? Right. The base is bigger. And you're not reciprocaling it over there, not flipping it over there. Yeah, so these were like making them so tiny where the opposite effect is on the other side of the graph. Interesting. I want you to think of, I don't know, 4 or 5 things that these graphs have in common though. Okay. End behavior. Good point. Good. They both have a horizontal asymptote. What else? Same 0 value. So like they both have the 0.01. Why is that? Because any number to the 0 is 1. Excellent. Anything else they have in common? Good. Their domain, they go on forever. Their domain is negative infinity to infinity. They go on forever. Both of them. Anything else? No, but I think you're onto something because they both start small and then they get huge, right? So what do you call a function that is going up? We actually have an I word that we used in chapter 1. Should we play hangman? It's an increasing function. It's going up the entire time, right? From left to right, it's an increasing function. Have we talked about the range? Do they both have the same range? We don't know. We're not sure. Yes? No? I see varying looks in the audience right now. The range, the y value. So did you notice that we're only getting certain types of y values when we make this graph? Greater than 0? Y value is greater than 0? Should we include the 0? Does it ever actually touch 0?
No.
How come we never got any negatives?
It's the horizontal axis.
Remember what we were doing? We were taking like 2 to the something.
Yeah, what is negative?
Right, because even if you use a negative power, it just makes it a reciprocal. It doesn't make it negative. So 2 to the something is never a negative number. Sometimes it's a fraction, but it never goes negative. Does that kind of make sense? Sweet. I'll tell you, my period 2 class is excited about this lesson. I hope period 3 and 8 are too. Good. Hey, let's throw a little twist in. Let's do a fraction to a power. Doesn't that sound fun? Yeah. Let's do 1/2. Maybe I'll make this one orange. Yeah, right? Right? Let's start with the easy ones, like what's 1/2 to the 0 power? Good. And what's 1/2 to the 1? Yeah? Is this hard for you to think of? What's 1/2 times 1/2, or 1/2 squared? 1/4. And what's 1/2 to the... Okay, so it's going to keep going down, 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 but never touching the 0, yes? Okay, now we have to think a little harder. What would 1/2 to the -1 be? That was really confident. 2, because you reciprocalize that, right? It would be 2 over 1 to the 1 power. So it's 2. 2. 1/2 to the -2. You okay with that, guys? So it's kind of like doing 2 squared. 4! Okay. Any guesses? 1/2 to the -3? 8. Can't fool you, kids. All right. So connecty. Well, that's a little different, isn't it?
Flip.
Yes. What kind of flip? I would say it is a horizontal flip, but over the y-axis, over a vertical line. Absolutely. And that sort of makes sense because 2 to the -x, if you can see how these are related, they're the same thing. That negative is a reflection over the y. That's fascinating. I can see it in your eyes. You're fascinated. Good. Good. Can you help me describe the end behavior? What happens as x's get negative huge? Y is, yes, goes on for infinity. What happens when x gets positive huge? Shrinks, 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 shrinks. It never gets to 0, but it wants to. Right? And actually, did you notice the domain of this function compared to the domain of all the ones we've graphed? What's the domain? One half to the what? What kinds of stuff can you put in that exponent? Anything. You can do positives, negatives. You can even do decimals. That's a little weirder, but all real numbers. And the special note sheet told me to do it in interval notation, so I always listen to my note sheet. And how about the range? Still greater than 0, even if it's a fraction base. Yeah? Do you know what it means when it says all functions on this page are continuous? Is that true or false? Do you know what that means? They continue on forever. They both have arrows. And okay, this isn't technically at all, but the layman's definition is you can draw the whole thing without ever picking up your pencil. Okay, so it doesn't have any holes. It doesn't have any skips. It doesn't have any discontinuities, is what they call it. So yes, they're all continuous. They also happen to go on forever and ever in both directions. Yes! Do you love logs too? I'll make you love logs. That's a promise. Yeah. You guys know what E is? No, E is just another number. Yeah, okay. Do you guys have an E button on your calculator? Why don't you check it out? Good. And so some of you are typing your E key. Some of you have an E to the something key. You could always type E to the 1. Will you find your E key and tell me what E equals? Yeah, that's all I usually remember. It's kind of like pi. It just goes on forever. It's irrational, okay? And it's this fancy number, right? And just like pi, the first time you heard about pi, you're like, what's the point of pi? And then it turns out that pi is immensely useful, right? Like it's used in trig and it's used in geometry and all kinds of junk. Well, it turns out that E is an immensely useful number too. You just don't know it yet. So let's first just talk about the number. That number is between what two integers? Good. Between 2 and 3. And so the graph, e to the x, should look kind of like 2 to the x, kind of like 3 to the x, only it would be like sandwiched somewhere between those. And sandwiched is an actual mathematical term. Sandwiched between those two graphs. Yeah. Let's just quick draw a 2 to the x and a 3 to the x. How long does that take you? Good. There's my 2 to the x, okay? Oh, we haven't done a 3 to the x. Here? Just throw down a 3 to the x too. Pretty nice. I bet you wish you brought your colored pencils today, don't you? Yeah. Yeah. All right. So now our e to the x, I'll make it pink. It is going to be sandwiched between those. So e to the 0, anything to the 0 is 1. E to the 1 is going to be like 2.71828. So it'd be like right there. And then, so basically, I'm just going to make it up. It's going to kind of do this. And it's probably going to be a little closer to 3 since the number e is a little closer to 3. That didn't go well. It's supposed to be sandwiched here. So there's e to the x. Do you feel comfortable just knowing that e is a number? It's just a number between 2 and 3. It's nothing mind-blowing, although it is awesome. They called it the natural exponential function because I told you that e would actually have some purpose in life, and it often happens in nature, like deer populations and all kinds of strange things in nature follow this number. It's amazing to me. I love it. We're going to try doing some transformations. If you still have your little rectangular tan sheet, if you ever thought that was useful, you could pull that out. But we're going to try to do some transformations to e to the x. Just a reminder, anytime it says natural exponential function, it's talking about e to the x. And we're going to switch this baby around. It's not going to be just like the normal e to the x function. I want to move that horizontal asymptote that used to be where? Where did the horizontal asymptote used to be on e to the x? It was always on 0, right? Y equals 0. Where do I want to move it? I want to move it to 3, it says in the problem, right? So I guess that would be moving it up, right? So I want to move it from y equals 0, where it normally is, up to y equals 3. What kind of transformations that's going to be? A shift, a vertical shift, up 3. Good deal. Where is the y-intercept usually? 0, 1. Usually it's at 1, because anything to the 0 is 1. But now we've changed it to 0, 5. What's up with that? Yeah. At first I was tempted to say that it must be added up by 4, but we already decided that we're only going up 3. So, Madison, you just said maybe it's a stretch, right? Right? Let's see if we can think this out. So if we're moving that asymptote up to 3, and our new function is going to be stretched out so that it crosses at 5, instead of, where would you expect it to cross if the horizontal asymptote was at 3? I would have expected it to just be 1 above the asymptote at 4, but now it's going to be up at 5. So how much further away is it getting? It's like twice as far away as we would have expected. Does that make sense? Not all of us. Not all of us. If all we had done is shifted it up by 3, every single point would have gone up by 3. So a point that used to be at 1 would go up 1, 2, 3, and it would be up at 4. Did that help at all? Like points that used to be at 0, 1 are now up at 0, 4. But if you think of this as the new axis, we expected it to be only up 1, but it's actually up 2. And so we have to think, since we're stretching it up, we have to multiply by something. It was up by 1, but we stretched it up by 2, so that's where we're getting the multiple of 2. We're stretching it vertically by 2. I know that's still a little iffy. We'll practice it some more. So this right here tells us that we're going to have a vertical stretch. Wow. By 2. Stretch by 2. Okay. Okay, if you can just believe us on this, how is that going to make our function look different? It's not going to just be e to the x anymore. It's going to be what? 2e to the x. That would get our vertical stretch. I heard you say it. Good. And plus 3 to move it up by 3. Yeah? Kind of makes sense. And like I said, you'll get to practice that some more. I've already put an example of this one-to-one property on here, but I thought I'd make up another one so we could actually talk through it. I'm going to do something like this. I'll do like 2 to the x plus 1 equals 8. And some of you could probably solve this in your head. Okay. Kind of our strategy is going to be to convert both of those numbers to the same base, because I'm not even going to give you any trick questions this time. Did you notice that these are both 2 to the somethings? Like 8 could be written as 2 to the what? Yeah, 2 times 2 times 2. So 2 to the 3. And this one-to-one property just says if you have 2 to the something equals 2 to the something, then the somethings must match. So the x plus 1 must equal the 3, which means x equals 2. That's the idea on those problems, so it's not anything earth-shattering. You just want to put it so they both have the same base. You okay with that? Okay. And then the formulas that I have next, I just wanted to remind you, because I'm sure that you've seen these before, but I just want to remind you what each of the letters stands for, and I think you'll be good to go with applying them to the problems. First of all, compound interest. Have you seen both of these equations before? Have you heard of PERT? Did you ever learn that last year? Maybe not. Some of you are nodding and some of you are shaking. So, okay, some of you remember. And how about this one? The p times 1 plus r over n to the... Yeah, these are used with word problems. This one is used if it says it's compounding monthly or compounding daily or compounding yearly or something, okay? But this one is used, anybody know if it says compounding what? Say that again. It's actually like every millisecond. Actually even better than every millisecond. It's like, kind of. They call it continuously. Continuously. Compounding continuously. Which sounds exciting to me because I would like to be earning interest every millisecond. Actually more than that. Okay, so I just promised that I would tell you what each of these letters stand for and throw some problems at you in the assignment, see if you can do it, okay? Okay, you just show me if you can do it. Anybody know what A stands for? We're investing some money at a certain interest rate, and what does A stand for? The amount after the time period. So some time passes and you got some more money, right? So A stands for that final amount after you've collected all your interest. P. It starts with a P. Close. Principal. Who the heck knows what principal means, though? It means the initial amount that you invest. I suppose you could use an I. A capital I hope. If lowercase, you'd think it's imaginary. P is principal. What do you think R stands for? Rate. It's the interest rate. Oh, maybe that's why they don't use an I. What are you complaining about? Oh, I didn't give you enough room. I'm terribly sorry. I understand if you never want to nominate me for Teacher of the Month again. They're already down there, so... Oh, you're so sweet. Interest rate, you have to put it as a decimal, okay? As a decimal. N? Oh, nope, you don't even have to do. Like, if the interest rate was 3%, 0.03. Yep. Anybody know what N stands for? That's the toughest one. You knew that one! That is Andrew. For the record, Andrew knows what N stands for. It means the number of times per year, because this is, since the R is an annual interest rate, the N is also in years. It's the number of times per year that you're getting your interest. So if I told you your interest was being added monthly, N would be 12. Weekly? Careful. Maybe you need to jot this down. How many weeks are in a year? 52. Okay. All right. Daily? 365. Unless it's a leap year. Right. So 365 or 366. Okay. Am I missing anything? Oh, what does E stand for? Oh, T. I'm sorry. T. What is T? Time. Time. Yeah, and actually, this is also in years, okay? All three of these things are in years. The annual interest rate, the number of times per year, and the T is in years. And what does E stand for in the PERT? Itself. Good answer. 2.71828, blah, 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 right? That was kind of a trick question. 52 weeks in a year. All right, we got a little science, which I know so much about. I'll try to fake it anyway. Radioactive decay, exponential decay. That's probably one of those functions that's going down, 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 right? Like our 1/2 to the x. What's that? Yeah, like the depreciation on your car's value. Absolutely. Absolutely. Oh, that's smart. In this case, they're usually talking about, is it carbon 14? Okay. Yeah, I don't know what I'm talking about either, but that's how they like tell how old your bones are after you're dead. And okay, dinosaur bones after they're dead. They can date them using radioactive decay. Anyway, I'll stop talking. A stands for the amount after the time period, which is usually what they're trying to figure out. Oh no, I said that wrong. The amount after the time period is usually what they can measure, right? They dig up a bone and they can measure how much is there after the time period. I suppose what they couldn't measure is little a. They probably didn't know how much there was at the beginning. Or did they? Am I doing a bad job of faking it? Initial amount of carbon 14 or whatever sort of radioactive material we're measuring. No, I suppose it would be the time that we really want to know, isn't it? Because we're trying to date this thing. H stands for half-life, which those science people know. Like, they could tell you that every 3,600 years you'll lose half of your carbon 14. Oh my gosh, I know nothing about science, I apologize. But H stands for half-life, which they'll give you in the problem, because even I don't know it, so, okay. Just a little hint. Sometimes half-lives are really long and they're in years. Sometimes half-lives are really short and they're in seconds or days. So what you should know is that your time and your half-life should both be in the same unit of time, just depending on the problem. Hopefully that's enough information that you can try some of those word problems. Last thing, the little summary of the day. I was hoping that you would kind of pick up on, there's some types of exponentials that grow, right, the increasing type. And there's some types of exponential functions that decay, like the value of your car. And it definitely has to do with the value of a. Sometimes a to the x grows, sometimes a to the x decays. Do you know when it's going to be growth and when it's going to be decay? You do. Okay, so tell me, when the value of a is what, we're going to see growth? The people who said greater than 1 were onto it. Greater than 1, because like 2 to the something or 4 to the something, that gets huge. What kinds of numbers, you can even look back, what kinds of numbers will give you a decaying function? Less than 1, like the fraction-y ones. Like the less than 1 fraction-y ones. So technically, we're going to keep that between 0 and 1. But as long as that amount in there is less than 1, it's going to be a decay function. That was crash course on exponential functions and their applications. Do you guys have any questions that might help the future children of Mrs. Backlund's class? Okay. So your assignment is over on the board.